We live in a world just hacked with engineering marvels. We're surrounded by them. Things that defy gravity, that withstand unbelievable pressure, that move at incredible speeds. But all of it comes down to one simple, critical thing: how well you join two pieces of material together. Because that connection point, well, that's always the first place things go wrong.
I mean, really think about that. What is actually stopping an airplane that weighs hundreds of thousands of pounds from just falling apart at 30,000 feet? It's definitely not magic. It's a whole series of connections, thousands of them. And every single one has to be perfect. But perfection, that's a tough thing to nail. And the enemies you're fighting are invisible, they're relentless, and they're always, always waiting for just one tiny mistake. And these are the enemies. We're talking about microscopic terrors that grow silently over time. They're born from the constant stress and vibration of just being in the air. These are the weak points, the vulnerabilities where all the massive forces of flight just gather together, almost like predators attacking the structure's integrity. This is the slow, quiet decay of the material itself. And listen, when you're dealing with advanced stuff like aluminum alloy 6013, the very skin of an aircraft, failure is just not an option. Okay, so let's get into this. For decades, the go-to method for joining these critical aircraft parts was riveting. Old school. But that technique, it carries a hidden and pretty dangerous cost. Take a close look at this quote. Every single rivet, yeah, it's holding things together, but it's also creating a potential starting line for a catastrophic crack. It's a fundamental flaw baked right into the system. So of course, engineers turn to something more elegant: welding, fusing metal into one seamless piece. But this opened up a whole new can of worms and a whole new set of dangers. Welding thin, high-strength aluminum it's like performing surgery on the edge of a razor blade. You have to melt the metal to join it, right? But the very act of melting it threatens to destroy its strength. It is an incredibly delicate balancing act. And this right here, this is the heart of the welder's dilemma, a perfect catch-22. If you use too little heat, they call it underwelding, the bond is weak and you compromise the entire structure. But if you use too much heat, overwelding, you literally burn holes straight through the fuselage. Too little, you fail. Too much, you fail. Perfection is the only way forward.
So how in the world do you hit that perfect mark? You can't just count on having a steady hand. You need a smarter tool, a piece of tech that was literally designed for an impossible task. So you bring in a process with the power to control heat with microscopic precision. This is the high-tech gadget for the mission. Instead of a constant, brutal stream of heat, pulsed-TIG welding zaps the metal with these alternating pulses of melting and cooling. What that does is it dramatically lowers the overall heat exposure, which protects the alloy's strength. But here's the thing: just having a fancy tool isn't enough. You have to know the exact settings, the secret combination. Finding that one perfect combination across all these different variables, it's like trying to find one specific grain of sand on a massive beach. Just searching randomly would take you forever. You need a map, a systematic method for cracking the code. And that map has a name, the Taguchi method. But it isn't just a formula, it's more like a philosophy. It's this powerful investigative strategy that lets engineers test a huge range of possibilities with a really small, strategic number of experiments. It lets them zero in on the best solution with, honestly, ruthless efficiency. It's the system you use when you have to find an unbreakable code. And here is the battle plan. First, you figure out the key variables, the things that actually control the weld's quality. Then you design a matrix of tests, a very specific set of experiments to run. You execute those tests with absolute precision, and finally, you analyze the data to uncover the hidden pattern, the one true combination for success. So, with the protocol locked in, the mission starts. The team gets ready to run a series of carefully designed tests, and every single one is a step closer to the answer. The tension is high, you can bet on that, because the data from these experiments is going to decide everything. Okay, so these are the 4 dials that have to be turned to their exact positions. You've got peak current, that's the high point of the energy pulse, base current, that's the low point, pulse frequency, how fast the pulses are coming, and pulse on time, basically the percentage of each cycle that's at peak power. 4 variables, all connected, all critical. This is the mission map. It's called the L9 orthogonal array. It lays out 9 very specific experiments.
Each row is a unique combination of those 4 variables we just talked about, and they're strategically chosen to give the most information with the fewest tests. Every weld they make is a new data point, another clue in this huge puzzle. And the results start rolling in. The tensile strength, that's the force it takes to pull the weld apart, measures an impressive 272.2 megapascals. That's a really strong result. But then, another test, with different settings, comes in at only 223 megapascals. A huge drop in strength. The data is proving it. Getting the right combination is everything. Now, it's just a matter of finding the absolute best one. So, the 9 experiments are done, the samples have all been pulled apart, their breaking points measured and recorded. All that data gets fed into the model, and the statistical analysis starts its hunt for the one combination that delivers maximum strength. The code is about to be cracked.
The analysis isolates the impact of every single variable, and it calculates the perfect level for peak performance. And after all those calculations, a single, perfect formula rises up out of all the noise.
First up, the peak current, the maximum power of the pulse. The data points to one single number, 170 amps.
Next, the base current. That's the gentle background heat that keeps the metal ready. It has to be perfectly balanced at exactly 85 amps.
Then you've got the rhythm of the weld, the pulse frequency. That has to be set to a steady 4 Hz, 4 pulses every second.
And finally, the pulse on time, how long that peak power is applied. The perfect duration, 50%. And just like that, mission accomplished. These 4 numbers are the code, the precise, repeatable formula for the strongest weld possible, a solution that wasn't born from guesswork, but from a rigorous, methodical investigation.
You know, this whole quest for a perfect weld, it's just one of thousands of quests, just like it, happening every single day in every field of engineering. It kind of makes you wonder, doesn't it? How many other invisible calculations, these hidden formulas, and meticulous experiments are quietly at work all around us, holding our world together and keeping us safe?